A block of mass 24 kg is on a rough horizontal table. As soon as I read rough horizontal table, I know that there's some frictional force acting on the block, right? And then it goes on to say a force F is applied to the 24 kg block at an angle of 35 degrees to the horizontal. The 24 kg block experiences a force of friction of 7 Newton as it moves. We are even given the frictional force, right? It goes on to say that the block is connected by a light inextensible rope which passes over a light frictionless pulley to another block of mass 12 kg, clearly indicated on the sketch, which hangs vertically as shown in the diagram below. And we are told to ignore the effects of friction, as we always do. And then it goes on to say that the 24 kg block moves to the left at a constant velocity. So the 24 kg block is moving to the left. Let's just indicate that. And then now 2.1 says state Newton's second law of motion. We know that F net is equals to ma, and if we make a the subject of the formula, we get a is equals to F net divided by m. So clearly here, if you apply a F net on an object, the object will accelerate in the direction of the net force with an acceleration that is directly proportional to the applied force and inversely proportional to the mass of an object, clearly. And then you can also say that F net is equals to delta P divided by delta T. That is Newton's second law in terms of momentum. And it will say that the net force acting on an object is equal to the rate of change of momentum of the object. And then now we can move to 2.2. 2.2 says, what is the resultant force acting on the system? If you pay attention to this statement here, it says that the 24 kg block moves to the left at constant velocity. Constant velocity implies that our acceleration is equals to 0. If acceleration is equals to 0 and F net is equals to ma, then F net is equals to 0 newtons. So 2.2 we have 0 newton. And then now we can move to 2.3. 2.3 says draw a fully labeled free body diagram to all the horizontal forces acting on the 24 kg body, right? So that's our free body diagram there. And then we have the tension as a consequence of the string attached to the 20 kg block, right? And then we also have friction that is going to the right because our object is said to be moving to the left, right? And then our force applied is supposed to be moving to the left, right? So we have force applied here. I'm trying to make the error of the force applied to be equals to the tension plus the friction, right? Because these forces are balancing out. As a consequence, our object is moving at constant velocity or with an acceleration of 0. So now we can go to 2.4. Before we go to 2.4, if you want to support the channel, please check the link on the description there. And then 2.4 is saying calculate the tension in the rope, right? For our 24 kg block, we don't know what the tension is. We know what the friction is, but we also don't know what the force applied is, right? But for our 12 kg block, let's have a free body diagram for our 12 kg block. We have the tension that is pushing up, and then we have the weight that is pushing down, right? And then we know the weight, obviously, because we have the mass. The only unknown variable is the tension. So here, clearly, it will be easier for us to use the 12 kg block to find the tension versus the 24 kg block, right? Because on the 24 kg block, at this point, we have two unknown variables. So for the 2 kg block, so I'm writing 2 kg, we have F net equals to the mass multiplied by the acceleration. So it's just two forces. The weight minus the tension is equals to ma. These two forces are said to be equal, right? So the order really doesn't matter, but usually I start with the bigger force and subtract all the other forces. So what is the weight? The weight is 12 minus 9.8 minus tension being equals to this is 12 kg, not 2, being equals to 12 multiplied by 0, because we know that it's moving at a constant velocity. So we're gonna have minus tension being equals to minus let me just put that in my calculator real quick. Don't want to embarrass myself, right? So we have 12 multiplied by 9.8, that is 117.6. so our tension is basically 117.6 newtons. It says let's calculate the tension, right? So we can put a direction here. So for the 12 kg block, it will be to the left, right? And then for the 24 kg block, it will be to the right. So let's do 2.5. 2.5 says let's calculate the magnitude of force F. So now if we come back to our free body diagram for the 24 kg block, now this unknown variable of tension, we now have it, right? So we have tension, we have friction, we just need Fa. So again, we're gonna say 24 kg, and then we have F net equals to ma, and then force applied, we see that it's supposed to be equal to the tension plus the friction, right? So it's bigger than those individual forces. So we're gonna have F applied cos of 35 plus minus tension minus friction is equals to ma. Now let's talk about this cos 35. So the force applied is at an angle of 35 degrees to the horizontal, right? We want to resolve it to the x along the x-axis. On a flat surface we use cos, and then on an incline we use sine. Clearly we on a flat surface here, so that's why we say in Fa cos of 35. So it will be Fa cos of 35 minus 117.6 our tension, and then minus 7 is equals to 24 multiplied by 0. Why am I saying minus 7? Look here, we are told that the frictional force is 7 Newton, right? So from here, what are we gonna have? We're gonna have Fa cos of 35 equals to 24 multiplied by 0 is 0, right? And then we take in minus 117.6 and minus 7 to the right hand side. We're gonna get 124.6. We divide both sides by cos of 35. So 124.6 divided by cos of 35. So I'm getting a force applied here of 146.1343 newtons to the left. We are only actually it's not to the left, it's at an angle of 35 degrees, right? Plus even the question only needs us to find the magnitude of force F. So 2.6 says force F is now removed. Does the magnitude of the normal force increase, decrease, or remain the same? So let's find a formula for the normal force so that we can see what happens. So here on our object, when we're talking about the normal force, we now pay attention to the forces acting on the vertical, right? The normal force is pointing up, obviously, and then we have the weight going down, and we have F applied to the Y, right? So clearly from these forces, the normal force is supposed to be equal to the weight plus FAY. So if you remove this force, the normal force goes down. Clearly, the normal force will go down. So here we're gonna have decrease. So let me show you something. It will not always go down when you remove a force. Let's say this force, the force applied was acting up, right? Then we were gonna have the normal force, and then F applied Y, and then down we still have weight. So from this sketch here, we're gonna have the normal plus FAY equals to the weight. So the normal is equals to the weight minus FAY. Clearly in this case, if you remove FAY, the normal would go up. I'm going to post other questions from this question paper. So make sure you subscribe so that you don't miss any of that. So let's look at the question we have here. It says an 8 kg block on a rough horizontal surface connected to a 2 kg block by a light inextensible string passing over a frictionless pulley as shown below. The 8 kg block moves at a constant speed. So when we hear constant speed, we know that the acceleration is equals to 0 meter per second squared, right? So this implies that the F net acting is equals to 0. And then it goes on to say when pulled by a 29.6 Newton horizontal force to the right, the frictional force acting on the 8 kg block is 10 Newton. There we have it. The first question says, state Newton's second law in terms of motion. Assuming that you already know what that is, so I'm just going to move on. We have 2.2. 2.2 says, draw a labeled free body diagram for the 8 kg block. So if you have went through questions like this, I'd advise you to pause and then do the question by yourself, and then you then watch me do it. So the free body diagram on the 8 kg block. Okay, there we have the 8 kg block. It's lying on the horizontal surface. Because it's lying on a surface, the surface is exerting a normal force up, right? Yeah, so there we have it. And then gravitational force is always acting. Yeah, so we're gonna have Fg or W for weight, whatever you wanna call it. And then we have our force that is being applied there of 29.6 Newton. So I'm gonna put that there, and then they say that friction is acting, so we're gonna have Fr, and then it is also it's connected to a 2 kg block through a string, so we have tension, right? So I'm just gonna put it there. So yeah, there we have it. Those are the forces acting on the 8 kg block. The tension and the frictional is equals to the F that is being applied, right? And thus it is moving at a constant speed, like they stated. So let's carry on. Let's move ahead. Says 2.3, calculate the tension in the string. So let's look at the 8 kg block. So let's say 8 kg block. I'm not choosing 8 kg, the 8 kg block, because it's the one I like the most. 8 is not my favorite number. I'm choosing it. I'm just trying it out. I will write all the given information for the 8 kg block and then see if I get to the answer. If I don't get to the answer, I'll then use the 2 kg block. So I'm not choosing the 8 kg block because I like it so much. But then usually in questions like this, if you have a 2.1, the answer for 2.1 helps you answer 2.2, and the one from 2.2 helps you answer 2.3. So because 2.2 says the free body diagram of the 8 kg block, it's most likely that 2.3 you will be using the 8 kg block. But then let's just go ahead and see. So the law we're sticking to is Newton's second law of motion, obviously. So we're gonna have F net. Okay, F net equals to mass
multiplied by acceleration. And then we also know that F net is equals to the first force, the second force, and then some force n, right? So what are the forces acting on the horizontal on the 8 kg block? We know that from 2.2 we have the force applied, we have the tension, and then we have the friction. So if we write that down, we're going to have this force which is being applied plus the tension force plus the frictional force equals to 8 kg multiplied by 0, right? Because that is we have an acceleration of 0 because it is moving at constant speed. So what is F? F is given to us is 29.6. What is T? T is our variable of interest. So there we have T there, and then plus friction, right? Friction opposes the motion. It's opposing the motion like the tension. So we're going to put a negative value there. It says that the frictional force is 10 Newton. So we're going to have minus 10 equals to 0, right? So 29.6 minus 10, that is 19.6. So we're going to have 19.6 plus T equals to 0. Take 19.6 to the other side, you get T equals to minus 19.6 Newton, which makes sense because T is opposing the motion, so it's supposed to have a negative value. So let's move ahead. For 2.4, they say that the force we have is now increased to 15 Newton, right? So we're going to have F equals to 15 Newton, and then there we have it. And 2.4.1, 2.4 says apply Newton's second law to each block and calculate them. 2.4.1 then says magnitude of the acceleration of the 8 kg block. Okay, so let's start with the 8 kg block and see if we can get the acceleration using the 8 kg block only. And then if we cannot, then we'll then involve the 2 kg block. But then let's start with the 8 kg block. So the 8 kg block, we're sticking to the basics. We know that F net equals to MA. This is equals to the sum of all the forces acting on the object. So from F1 to some Fn, n being any number of the forces we have. So F1, the force being applied, 15 Newton. There we have it. And then we have tension opposing. So we have minus T, and then we have the frictional force, which is said to be 10 Newton, right? So that is minus 10, and then equals to 8 multiplied by acceleration, right? And then and then this will be our equation 1, because now we have 2 variables, right? So we need another equation. If you have 3 variables, you make sure you get 3 equations. If you have 4, you get 4 equations, and then you can solve. So another equation, we'll get it by using the 2 kg block. The question sort of gives it away because it says apply Newton's second law to each block. But then even if it doesn't say that, if you're trying to find acceleration and tension, and then you find yourself in a situation where you have 2 variables, you have to use the other mass or the other block, the other whatsoever, to find the second equation, and then you can solve simultaneously. So let's go ahead for the 2 kg block. For the 2 kg block, there's 2 forces acting, the tension and gravity. So we're gonna have the tension minus gravity, which is equals to MA, right? The mass is 2 kg, so let me just go ahead and put 2, and then that's been multiplied by A, which we don't know what it is. And then our T equals to minus Fg is the mass multiplied by 9,8, right? So there we have it. This is equals to 2A. So we're gonna have T minus 19.6 equals to 2A. This is our equation 2. Some people like complicating their lives. They they want to solve this simultaneously by making t the subject of the formula and then substitute on the other equation. But then the way I like doing it is like on the first equation, look at this part, we have minus t, right? And then on the second equation, we have t. So if you add these two equations, t is gonna disappear, and then you're gonna actually it's not going to disappear. That's technically wrong. They're going to cancel out. So you're gonna be left with only a, and then you can just solve for acceleration. So let me practice what I preach. So equation 2 plus equation 1 will give you, so I'm adding 2 to 1. So I'm gonna have 50 minus t minus 10 plus okay, let me, yeah, and then t minus 19.6, and then that's it, equals to 8a plus 2a. This is equation 1, and then I'm adding equation 2. Okay, so t and t are going to cancel out, like you see. So here on this side, I'm gonna be left with 50 minus 10 minus 19.6 equals to 10a. This implies that a equals to 50 minus 10 minus 19.6 divided by 10. Let me put that into my calculator real quick. So 50 minus 10 will give you 40 minus 9.6 minus 19.6 divided by 10, and then I'm getting an acceleration of 2.04 meters per second squared. Yeah, so there you have it. That's how you solve this problem. Let's carry on. Last but not least, 2.4.2 says calculate the tension in the string. We have this equation 1 here. There you have it, and then we have this equation 2 here, and then we're supposed to find acceleration. So we can just sub in the t we found on 2.4.1 in any of these equations. The second equation looks a bit simple. It's easy on the eye. It doesn't look as complicated as the first one. So let's sub t on the second equation. So we have t minus 19.6 equals to 2a. So t equals to 2. We're saying that a is 2.04, right? And then we add 19.6. Let me put that in my calculator real quick. 2 multiplied by 2.04 plus 19.6. That gives me 23.68 Newton. And that's it for this problem. We're done with it. Make sure you subscribe. I'm going to post other questions from this question paper, the May June from 2021. So we have a 20 kg block that is placed on a rough surface inclined at 30 degrees to the horizontal, and then we have a constant force F acting parallel to the surface that is applied on the block, so that the block moves up the incline at a constant velocity of 2 meters per second. So we have v equals to 2 meters per second, and then we have our acceleration that is equal to 0 meters per second squared, because it is moving at a constant velocity. And then it is said that the constant kinetic frictional force, so we have friction that is equals to 18 newtons x on the block, and then 2.1 says stay 8 newtons first law. In words, we know that a body will remain in a state of rest or motion at constant velocity unless a non-zero resultant force acts on it. And then 2.2 says draw a level 3 body diagram for the block. So I'm just gonna go ahead and do that. So that's our block, and then we are told that there's a F that is applied on the block, right? And then since it is resting on a surface, we have a normal force. So this is our normal force, this is our F applied, and then we always have weight, right? Regardless of anything else. And then we are also told that we have a frictional force that is opposing the motion at 18 newtons. So there we have our frictional force. So that's it for the free body diagram. We can move ahead and do 2.3. And then 2.3 says calculate the magnitude of force F. In question 2, more often than not, when we're answering any question, we'll start by saying F net equals to MA almost all the time. And then what is F net? F net is what we have on the free body diagram, right? So what we have is F applied plus all the other opposing forces. What are the opposing forces? First is friction, right? Because friction is always opposite the direction of the motion. And then the other force we have is FG parallel, right? Which is equals to MA. What is MA? We know that M is 20, and then we have deduced that the acceleration is 0 because it is moving at constant speed. So we're going to have F applied plus, and then we know that our frictional force is 18 newtons, so we're going to have minus 18 because it's opposing the motion. And then FG parallel, that will be the mass multiplied by gravity, so that will be 20 multiplied by minus 9,8, and then sine of the angle, because parallel on an inclined surface it is sine, and then perpendicular will be cos, and then on a flat surface it is vice versa. So we're gonna have the F applied equals to, I'm taking 18 to the other side, so I'm gonna have 18 plus 20 multiplied by 9,8 multiplied by sine 30 degrees. So if I put that on my calculator, I'm gonna get I'm getting 18 plus 20 multiplied by 9,8 multiplied by sine of 30 degrees, which is giving me 116 newtons. If you're new to the channel, please like the video and consider subscribing. And for 2.4, there's some statement there that says force F is removed when the block reaches point X. So now we only have the friction and the FG parallel. The block continues to move up the surface and comes to rest momentarily at point Y before it starts sliding down, right? Assume that the kinetic frictional force acting on the block remains at 18 Newton as it moves from point X to point Y. Write down the net force acting on the block as it moves from point X to point Y. So at point X, we know that F net equals to MA, but then now it is no longer moving at a constant velocity, so we cannot use mass and acceleration to find the resultant force, but we can use the components of the forces themselves, right? So we can have F net which is equals to frictional force plus FG parallel, right? Because the question says F net, and then these are the only forces that are still acting. What is this equals to? This is equals to minus 18 plus 20 multiplied by 9,8 minus 9,8 multiplied by sine 30 degrees, which we know that it is equals to 116 newtons from 2.3, right? Hence, That's why the question says write down the net force. It doesn't say calculate because you've already calculated it. But then maybe in an exam kind of situation, you can get confused. So that's why I just decided, okay, let's just calculate it again. But then there was really no need to calculate it again. And then 2.5 says calculate the distance between points X and Y. As soon as you hear about distance, I'm thinking equations of motions. That's what I'm thinking as soon as I hear about distance. So we need some distance, delta X, right? So this delta X, our unknown variable. We have VI, which is equals to 2 meters per second, because it is said that it is moving at a constant velocity of 2 meters per second. And then what else do we have? So we have delta X, we have VI. Another variable we can extract is acceleration. We can say that F net equals to MA, right? And now we know what F net is. F net is minus 16 newtons. This here was supposed to be minus 16 newtons because F net is opposing the motion. So we have minus 16 newtons equals to 20 kgs multiplied by acceleration. So our acceleration is equals to minus 116 divided by 20. Which is giving us minus 5.8 meters per second squared, right? So now we have delta X, our unknown, we have VI, we have acceleration, and we know that VF is equal to 0. Yeah, because at Y, they're saying that it stops momentarily, right? And then after that, it slides down. So which equation of motion have these 4 variables? Because if we can find an equation of motion that has these 4 variables, then we can use that equation of motion to determine delta X. So we know that that is VF squared equals to VI squared plus 2A delta X or delta Y, whatever the axis you're dealing with. So this is 0 squared, which is equals to 2 meters per second squared plus 2 multiplied by minus 5.8 delta X. So we take 2 squared to the other side, we're gonna get minus 2 squared, because 0 squared will just fall off, and then we're gonna have minus we're gonna have 2 multiplied by minus 5.8 delta X. Make delta X the subject of the formula. Then we get minus 2 squared divided by 2 multiplied by minus 5.8, which is gonna give us, let me put that in my calculator real quick. So we have 2 squared divided by 2 multiplied by minus 5.8, and that is 0.34 meters. So the distance from X to Y is 0.34 meters. So we have 2 blocks here, one of mass 2 kg and the other one of mass 5 kg. And then there's a force applied on the 5 kg block at an angle of 20 degrees. And then we are told that the 2 kg and the 5 kg blocks, they both experience kinetic frictional forces, right, of 10 Newton and 15 Newton respectively, right? So the 2 kg block experiences a kinetic frictional force of 10 Newtons, and then the 5 kg a kinetic frictional force of 15 Newton. That's what respectively is basically telling us. And then the first question, 2.1.1, says let's state Newton's second law of motion. Again, Newton's second law of motion in words, it just states that when a non-zero resulting force is applied on an object,
the object will accelerate in the direction of the non-zero resultant force with an acceleration directly proportional to the F net and inversely proportional to the mass, right? So we know fully well that F net is equals to ma, and then in this equation, if you make acceleration the subject of the formula, you basically get the definition, right? Acceleration will be equals to F net divided by the mass. Clearly in this case, the acceleration is directly proportional to the F net and inversely proportional to the mass, right? And then 2.1.2 says, let's draw a labeled free body diagram for the 5 kg block. So here's our 5 kg block here, right? So free body diagram, we denote the body with a dot, right? So there we have our dot. We are told that there's a force applied, right, at an angle of 20 degrees relative to the horizontal. So let's have that force that is applied, right? So we have FA, A denoting applied. And then no questions asked. Any object on Earth will always experience FG, right? The force of gravity. So we have Fg. And then if that body rests on a surface, then the surface will exert a normal force on the body, right? So there we go, normal force. And then apart from the normal force, the 2 kg and the 5 kg block are connected by a string, right? So we must have tension, right? So we have tension there. We are also told that there's a kinetic frictional force acting on the blocks, right? So we can have Fr also acting to the left. So let's, do 2.1.3, which says that let's calculate the magnitude of force F. Force F is the applied force, right? That must be applied at an angle of 20 degrees to the horizontal to make the 2 blocks accelerate at 2 meters per second to the right. So in this situation, we need the acceleration to be equals to 2 meters per second. So here, we're trying to find the magnitude of force F that must be applied at an angle 20 degrees to the horizontal, right? So the force F that is applied, it's applied on the 5 kg block. So we're going to go to the 5 kg block and try see if we can get the magnitude of force F. So what are we essentially saying? We're saying that for the 5 kg block, right, F net is equals to ma, right? So now in place of F net, we can add the forces that are acting, and in place of ma, we have the mass and we know the acceleration. So which forces are acting? We know that along the horizontal, we are going to have Fa x, right? We're going to resolve the force applied along the x, right? And then now we're going to minus all the forces that are opposing the motion. Which forces are opposing the motion? Obviously, frictional force will be opposing the motion, and then the tension force will also be opposing the motion. And this will all be equals to ma. So what is Fax? Fax will be the force applied multiplied by cos of 20 degrees. We know fully well that if you want to find the x component, you take cos of the angle, and then if you want to find the y component, you take sine of the angle, assuming that you are on a flat surface, right? And then minus frictional force. The frictional force, it is said to be equals to 15 Newton, right? So minus 15 and then minus the tension. We don't know what the tension is, so we're just going to leave it like that for the moment. And then that is all equals to ma, right? We know the mass fully well. The mass is 5 and the acceleration, we're assuming that it is 2, right? The equation says, let's find the magnitude of the force F that must be applied if the blocks will accelerate at 2 meters per second. So now, let's go ahead and solve for Fa cos of 20 degrees, right? So we have Fa cos of 20 degrees being equals to, so we're taking minus 15 to the right hand side and minus tension, right? But then on the right hand side, we have 5 multiplied by 2, which is just 10. So we're going to have 10 plus 15
plus tension, right? So now we can divide both sides by cos of 20. So we're gonna get force applied being equals to 25 plus the tension divided by cos of 20. So it's easy to see now that we just need the tension. If we get the tension, then we basically have the force applied, right? So we have already used the 5 kg block. What we can do now is to use the 2 kg block and see if we can get the tension from the 2 kg block. So from the 2 kg block, there is the tension that is pulling it to the right and the frictional force that is pulling it to the left, right? So we're gonna have something of this manner. So we have 2 kg, and then in place of 2 kg, we know fully well that F net is always equals to MA. So now the force that is greater than the other is the tension, and then we're going to subtract the force that is opposing, which is the frictional force, and this will be equals to MA. But we know fully well what the frictional force is, right? It's given to us. It is said to be equals to 10 Newton, right? So we have frictional, which is 10 Newton. The mass is 2 kgs, the acceleration is 2. So the tension is basically equals to 4 plus 10, which is equals to 14 newtons, right? So here in place of T, we can substitute 14 newtons. So we're going to have 25 plus 14 divided by cos of 20 degrees. And if you put that in your calculator, you're going to get the force applied being equals to 41.50 newtons, right? And we basically done with that equation. Let's move to 2.2. 2.2 is into us. The Earth exerts a force of 1,842.5 newtons to keep a satellite of mass 200 kg in orbit around the Earth, as shown in the diagram below. We have a very fancy sketch there. And then the question says, let's calculate the distance above the Earth's surface at which the satellite orbits the Earth. So let's look at the information we have, right? We have the force that is acting between the Earth and the satellite. And then we have the mass of the satellite, right? Apart from the mass of the satellite, we have the mass of the Earth, because the mass of the Earth is a constant, right? So we have the mass of the Earth. And then now, what we're looking for is the distance between the Earth and the satellite, right? So we can use Newton's law of gravitational acceleration, right? Every body attracts every other body with a force that is directly proportional to their masses and inversely proportional to the square distance between them, right? So we're saying that F is equals to G, that G being a constant, right? And then mass of the satellite, mass of the Earth, and then divided by the distance between them. The distance between them will be equals to the radius of the Earth plus the actual distance between the Earth and the satellite, right? So we're saying that F is given to us, right? 1,842. So we have 1,842.5 being equals to that capital letter G, right? Which is a constant. It's 6.67 times 10 to the minus 11. So now the mass of the satellite is said to be 200 kgs. And then the mass of the Earth, right? 5.98 times 10 to the minus 24 divided by the distance between them, right? So we have distance squared, right? So now we're solving for the distance squared. It's easy to see. We know fully well that if we have A is equals to B divided by X, and you want to find X, you're going to cross multiply, right? You're going to get AX is equals to B multiplied by 1. So X will be equals to B divided by A, right? So we're going to apply the same idea in this situation. Our X is D squared, right? So we're going to have something like this. So we're going to have D squared being equals to this entire expression here, right? So let me just duplicate it for the sake of time, and then we dividing that by 1842.5, and then after you do that, you definitely take square roots on both sides, right? So you take a square root on this side, and then you take a square root on the right hand side too, and then you're gonna get a distance of 6,579,982.8 meters, right? So this is the distance between the Earth and our satellite. But then we don't want the distance between the Earth and the satellite. We want the distance above the Earth's surface at which the satellite orbits, right? Even if you look in the question here, it's in bold, right? The distance above the Earth's surface. So that distance will be equals to the distance we just calculated right now minus the radius of the Earth. This question has 5 marks, right? So if you stop here, you only have 3 marks. The other 2 marks is for you to subtract the Earth's radius from this value that we have. So if we do that, we can now say the distance above will be equals to 6,529,982.8 meters minus the radius of the Earth, right? The radius of the Earth is a constant, so we know fully well that that is 6.38 times 10 to the 6 meters, right? So your answer is going to be equals to 1.9998 times 10 to the 5 meters. Moons. Neptune's largest moon, Triton, circles its planet in a direction opposite to the planet's rotation. The mass of Triton is 2.139 times 10 to the 22 kgs, and it has a diameter of 2,706 kilometers. And then 3.1 says state Newton's universal gravitational law in words. We know that by formula F is equals to G m1 multiplied by m2 divided by r squared. We can see from the formula here that every body in the universe will attract every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square distance between them. And then now we can go to 3.2. 3.2 says calculate the gravitational acceleration an object will experience on the surface of Triton. So we want the gravitational acceleration. What is the formula of the gravitational acceleration? This is one of those formulas that you will most likely forget, right? But then it is said to be the gravitational acceleration will be equals to G m divided by r squared. This capital letter G being the gravitational constant, and then the mass is the mass of the object of interest, and then r is the radius of that object. In this instance, we're talking about Triton, a moon that is rotating around Neptune. So what do we have here? This will be equals to 6.67 times 10 to the minus 11. That is the value of G. And then the mass of Triton is said to be 2.1390 times 10 to the 22 kg. Now we have to pay our attention to the radius, right? We are told that the diameter of Triton is 2,706 kilometers, but then radius is only half of the diameter, right? So we're gonna have 2,706 divided by 2. We want the radius and not the diameter. But then hold on, the diameter is given to us in kilometers, so it's our job to convert it to meters. So we're gonna multiply this by 1,000. That is because in 1 kilometer we have 1,000 meters. So we're gonna square that, and then let me punch that in my calculator. So we have 6.67 to the minus 11 multiplied by 2.139 to the 22 divided by 2706 divided by 2 multiplied by 1000 squared, and that is 0.7794 meters per second squared, right? And then that's about it. We can move forward and go to 3.3. 3.3 says, if the space agency sends a robotic spacecraft of mass 15,000 kg to Triton, calculate the force of attraction when the robotic spacecraft is at a height of 50 kilometers above the surface of Triton. So we know fully well that F, like we have already said, is equals to G m1 m2 divided by r squared. So F will be equals to G is our universal gravitational constant, right? Which is 6.67 times 10 to the minus 11. And then we want the force of attraction between Triton and the robotic spacecraft, right? So let's say M1 is the mass of the spacecraft, which is 15,000. And then M2 is the mass of Triton, which is 2.1390 times 10 to the 22. The way you order the masses doesn't really matter, right? Because they will pull out, they're pulling each other with the same force. And then we divide by r squared. So what is r? We know that the radius of Triton is 2,706 divided by 2 multiplied by 1000. But the robotic spacecraft, it is said to be at a height of 50 kilometers above the surface of Triton, right? So here we're going to have plus 50 kilometers, and then we also multiply this by 1000, and we square everything. So let me just put that in my calculator real quick. So I'm getting a force of 10,842.08 Newton, right? So we have a toy trailer of mass 3 kg and a toy car of mass 5 kg, and then we have an applied force of 40 Newton, as you can clearly see on the left hand side. And then it goes on to say that both vehicles experience a frictional force while they're moving. The frictional force on the car has a magnitude of 4.9 Newton. So we have some Fr, which is equals to 4.9 Newton. And then the first question, 2.1.1, which says that write down Newton's second law of motion in words. It states that when a net force acts on an object, the object will accelerate in the direction of the net force with an acceleration that is directly proportional to the force and inversely proportional to the mass of the object. That is, the acceleration is directly proportional to the force, right, that is acting on the object, and is inversely proportional to the mass of the object. And then 2.1.2 says, what type of frictional force do the vehicles experience? So we are told that when these vehicles start moving, they are experiencing a frictional force, and we know that a frictional force that is associated with moving objects is kinetic friction. So we have kinetic friction. If they were stationary, then we were going to have static friction. And then 2.1.3 says, show by means of a calculation that the frictional force on the trailer has a magnitude of 2.94 Newton if the coefficient of friction is 0.1. So back to the definition. What is friction? Friction is given by the product of the coefficient and the normal force, right? And then we are told that the coefficient is 0.1. Now the question is, what is the normal force? The normal force is the mass multiplied by the gravitational acceleration, right? So we're going to have 3 multiplied by 9,8. And then if you put that in your calculator, you're gonna get 2.94 Newton, like the question says we should show. And then 2.1.4 says calculate the magnitude of the acceleration of the system. And then it goes on to say write down the separate equations for the two moving objects using Newton's second law of motion, and then calculate the acceleration, which is really unnecessary because we know that almost always when we're calculating the magnitude of the acceleration, we'll have to have two equations which will then solve simultaneously. But then, okay, without any wasting any time, let's start with the 3 kg mass. So we're gonna say 3 kg, and then we're sticking to Newton's second law, right? So we're gonna say F net is equals to ma. Now the question becomes, which forces are acting on the trailer, right? So on the trailer, we have the tension, right, from the car and through the string that is in between, minus all the forces that are opposing the motion. What are the forces opposing the motion? The forces that is opposing the motion on the trailer is the friction, and then that is equals to the mass by the acceleration. So the tension is unknown, but we know that the friction is 2.94. The mass is 3 kg, and the acceleration is also unknown. And then now for the 5 kg car, we know that the force that is pulling the car is the force applied, right, of 40 Newton. So we're gonna say F net equals to ma again, and we're starting with F applied, right, because it's the biggest force, and then we subtract all the other small forces. What are the small forces? We have tension that is opposing on the car, right, because it's being pulled by the trailer, and then we also have the frictional force acting on the car, which is all equals to ma. And then the force that is applied is 40 Newton, and then the tension is unknown, and the frictional force acting on the car, it is given as 4.9 Newton on the equation, right? So we're going to have 4.9, which is equals to 5 multiplied by A. So what we are going to do here, I want you to realize that here we have T, and here we have minus T. So if we add these two equations, T is going to disappear, and we're going to be able to solve only for A. So if we do that, we're going to get 40 minus T minus 4.9, and then plus T minus 2.94, right, equals to 5A plus 3A. So this is the left hand side of our first equation, and this is the right hand side of our first equation. So the equation is still balanced, but now T is disappearing, and we're gonna be able to solve for A. So we are saying 40 minus 4.9 minus 2.94 equals to 8A. So now if we make A the subject of the formula, we're gonna get A equals to 40 minus 4.9 minus 2.94 divided by 8. And let me just put that in my calculator real quick. So we have 40 minus 4.9 minus 2.94 divided by 8, and that is giving me an acceleration of 4.02 meters per second squared. And then now we have 2.1.5, which is calculate the force exerted by the string on the car. So now we're looking for the tension, right? We can take this equation here that we got when we were using the 3 kg mass, and then we solve for T because now we know A, right? Or we can take this equation here, but it's easy to see that the first equation is pretty much plain compared to the second one, so that's the one we're gonna use. So we're gonna say T minus 2.94 equals to 3A, but now we know what A is, so we're gonna get T equals to 3 multiplied by a, which is 4.02 plus 2.94. So we have 3 multiplied by 4.02 plus 2.94, and that is equals to 15 newtons. So the tension on the car is 15 newton. That is pulling the car backwards, right? And the tension that is pulling the trailer forward, it's also 15 newton. And then now the question goes on. It says the string is disconnected from the car and reconnected at a higher point to make an angle theta. So we can see that the tension was something like this, and now it's slightly going down. And then the question is, it goes on to say the horizontal force of 14 newton is again applied to the car to accelerate the system from rest as before. Alright, and then 2.1.6 says draw a free body diagram with labels of all the forces acting on the car. So because it's on a surface, we have normal force, and then we always have Fg, right? So there's Fg, and then it's been pulled by 40 newton force, so we'll have force applied, and then we have the tension by the string, which is now slightly at an angle. So there we have our T, and then that will be the free body diagram for the car. So 2.1.7 is asking us what is going to happen to the frictional force now that the tension is at an angle. So when the tension is at an angle, when we resolve it along the x-axis, right, it's going to go down, and then it will have a lower value, right? So let's go back to our equation for the 3 kg mass. So we know that we have T for tension minus the friction, which is equals to a mass by the acceleration. The mass is the same, the acceleration is the same. Now the tension has gone down, right, because it's now at an angle, but then we still need the mass and the acceleration to be the same. So how should the frictional force change? The frictional force also goes down, so that this equation is still true, is still balanced, right? So if the tension had went up, the frictional force would have to go up. So here we're going to say less than, because the frictional force need to also go down because the tension went down, and we still need to maintain our equality, right? And then for 2.1.8 it's saying what will happen to the frictional force on the car. So again, let's go back to the equation. For the car, we have the force minus the friction minus the tension equals to MA. The force is the same, right? So we can forget about the force. And then here we have the tension that is going down, right? And then M is still the same, and the acceleration is still the same. So how does this frictional force have to change such that this equality is maintained, right? So the frictional force has to be greater than, right? So let's have greater than for the frictional force. Why is the frictional force being greater than? It's being greater than because now the tension has went down, but the acceleration is still the same. So the frictional force has to go up so that the equality is still maintained. And then for 2.2, it says the planet mass has an approximate mass and radius 6.39 times 10 to the 23 kg and 3.39 times 10 to the 3 kilometers respectively. Calculate the approximate magnitude of the gravitational acceleration on the surface of Mars. We know that the gravitational acceleration is given by the big G multiplied by the mass of the planet divided by the radius squared. So what is the value of this big G that I'm talking about, the gravitational acceleration constant? That is 6.67 times 10 to the power minus 11. And then the mass is given to us as 6.39 times 10 to the power 23 kg divided by the radius squared, which is 3.39 times 10 to the power 3 squared. And if you put this in your calculator, it's gonna give you 3.71 meters per second squared, which is actually the gravitational acceleration of mass in real life.